let's try to do something that at least is interesting. I'm saying to you trivial things to most of you, but you know, still let's repeat. So we're living in an unprecedented society. So we are living in this data deluge. And I mean, you probably know this picture, but I mean, every minute of the day, night or day, because I mean, it's day somewhere on the planet. There were thousands of Amazon boats, Amazon packs delivered. And if you have small kids, there are thousands per day of chatting on WhatsApp with the other parents. I mean, that's data. How to sort, I mean, most of the information, of course, we don't care, but there is some signal in the noise. And if you think all the knowledge that has been produced by mankind in the history of civilization is doubled every year, less than 1 year. So how to deal with this? We believe that complexity is one of the instruments that we may use. And what is complexity? So this is a very legitimate question. So the traditional more is different paper says that when you have a lot of things, those things interact in some way and create something new. So you are a person, you have your personality. When you are in a crowd, probably you behave differently. A neuron is a cell. So a cell doesn't think. Well, we don't know what a neuron does, essentially, apart electric discharge. But when you have many neurons, well, you have a brain, and this brain thinks. When you connect people, we just listen to the talk of Cesar, smart things happen. So if we have to follow the ideas of another physicist, Stephen Hawking, probably if you're not a physicist, at least you look at The Simpsons. No? So this should know about this guy. So in physics, we know more or less everything on the elementary scale, but we don't know the laws with which these things interact. So it's like knowing how to do bricks, but we don't know the architecture very well. So I don't know what makes a church, a house, a swimming pool, a stadium, and so on. So, okay, this I must put this, but then I have to change all the other slides because you're expert at that. I believe that complex networks are a very good model, a very good way to represent this complexity. Why? Because you have the number of things, these things are vertices, and the interaction between them is the link, no? It's represented by a link. So this very simple mathematical representation is the skeleton, is the way in which you can describe what complexity is. And of course, I mean, this is plain, this is very simple graph. You can decorate the graph, you can put arrows on those. So for example, the World Wide Web is a directed network. So you go from one website to another one, but you don't go back along the same hyperlink. Phone calls are directed, many things are directed. That's just scratching the complexity of the mathematical object, because you can have network of networks, multi-layers, we have word expert of these things. You can have simplisher complexes and so on. But even simple graphs are pretty important. And whatever you study in complexity, so I have to move, thanks to Carlos, to real things, not to application of that. Whenever you're considering complexity, and whenever you use networks to describe this complexity, well, the same properties appear. So just restricting to these simple graphs, well, sorry, I missed the X in complexes, but I mean, you know what I'm talking about. Well, there are few properties that are always present there. So they are scale invariant, all these things, or they are heterogeneous, very much heterogeneous. They are small words, so there are systems that are fast to travel, will be very, how to say, fast on that. Strongly clusterized, so it's not, how to say, the same stuff if you travel everywhere. There are certain zones that are more dense, others are less dense. And not all the vertices counted the same. This is not democratic, I have to say. It's aristocratic if you want, but this is what happens. And more than that. So this is a talk, but it's also, how to say, a fun moment. We are celebrating Dirk's birthday. So let's have some fun. Okay, this is me some years ago. Can you spot me in the picture? This is Prima Media. So Carlos, which one? Say. Which one? This one? Up, down. Okay, move from 0, 0. Where they go? Did I? No way. So any third from the ball. 1, 2, 3. Santo, you're a genius. We knew. Everybody knew that. Okay, why? That many years ago. Why? Because, I mean, if you study one very simple thing in this classroom of boys, 8, how much we were told. We were 13 at the time. And you take Wikipedia, okay, you have this very nice distribution. So that's typical, no? And we know that's typical because this German guy studied these problems, and we know that there is an average height for those guys. And, you know, some people are taller, some people are shorter, but I mean, that's not that much. You may suffer for that, but it's not that much, okay? It's completely different when you move to the stock market. To the stock market and you ask, okay, what is the income of the people working there? What is the capitalization of the stocks that are traded there? Well, it's not at all a curve of this guy. And we know for another guy, this is one of the many Italians working in Switzerland. No? This is Wilfredo Pareto. So this we know that is absolutely heterogeneous. What does it mean? That when you're considering networks, well, and you're studying the size of a guy, okay, you have a short guy, you have a tall guy, but you know, the average is what you expect. But when you study, for example, the number of people on a social with as F friends, well, you have a lot of people with few friends, and you have just a tiny amount of the person in the social who have millions of friends, but these are orders of magnitude. It's not 20% more, 20% less. You know, it's 10 to the 6th more. So it's like having somebody in this conference room that is tall 2 millimeters or 10 kilometers. It would be strange, you know? So when we think about complexity and networks, we always constantly forget about that there are order of magnitudes going on in the time. It is very important, and this applies to COVID, applies to exponential growth, applies to all these things. So things can change, you know, in a second. And this is something you have to take into consideration. This is really a power law. No, we studied that. There has been some criticism about that, but this is true scale-free networks. The only problem you find when considering the data is the cutoff of the data. You can't expect a mathematical relationship to hold at every length scale for real in physics. There is the cutoff. You have to take care of this cutoff properly. So the second part, this is a celebrated paper by Milgram, and is on the small world. So you send to random person in the US a letter, and you give to them a target person that is in Boston, and see if they know, I mean, if one of their acquaintances, this guy or not. Otherwise, pass to somebody else. See the pictures, this seems to be Yellow Submarine, are the same years as the 60s. This is a paper of 1967. And this is a real chain. So starting from people working in a supermarket, you know, you have a carpenter, then people work in a library, and some jobs are disappeared, some linotypists, so people typing things, and then eventually this guy who's selling dress knew the guy working in a bank. So the point is that in this societal exploration, people are connected by just 6 degrees of separation on average, but typically in a very short distribution. And actually now it's much, much less. This is sorry, I didn't put the reference. I forgot yesterday when I made on the fly the slides. This is a paper by Boldi, Vigna, and some other guys, I believe Riccardo Beza Yates as well, analyzing the Facebook data. So the Facebook data, the main distance of separation on Facebook is less than 4, so 3.57. Okay, so this is the small world effect. Another effect that we seldom consider is the fact of the clustering. And in society and in the other systems, this comes out essentially for this simple mechanism. So in many cases, we may do this game now in this auditorium if you want. You can distinguish in a system 2 classes of things. So you can have persons and you can have papers they wrote together. So yellow circle are papers, and green squares are what I say. These are papers. So these are persons and these are papers. Okay. And 1, 2, and 3 happen to write the same paper A, but 2 wrote paper B with 5, and so on and so forth. Once we have this bipartite graph, you can project it very easily and build a network of users. So users are connected if they wrote a paper together. and networks of the papers. So papers written by the same person are connected with each other. So what do you obtain with this representation? Well, you obtain subgraphs that are complete. So this is a complete graph by 3. This is a complete graph by 2. This is another click. There is a complete subgraph. And those persons have something in common because they wrote something together. But also this paper must have something in common in the topic because they have been written by the same guy. So this is the elementary mechanism that create clustering in most of the social things. And how can you use that? So let's pass to the application that Carlos was asking yesterday. So this is one very nice paper, but by the group of Laszlo Barabashi, Kvanil Go, and other published on this PNAS in 2007, yes, on the DCSOM. And so you take some gene in the DNA of people was malfunctioning, could create diseases, and you connect the disease that they could create, okay, with this malfunction of this wrong way of reproducing of the gene in the cells. Okay, so this is the genome, and this is the phenome, the phenotypic effect that you have when this gene is duplicated wrongly. So in this case, you can build a network of diseases, a comorbidity network, and a network of cooperation of genes in some sense. So once you are in, unfortunately, one of these situations, and this is because of wrong copying of your genome, you know that you're very, very likely to develop one other of these diseases. So you can do precision medicine. Okay, so networks show exactly what's going on there. I was thinking that Cesar was going to present same stuff that you can do in the economic development. So I don't have slides for that, but Cesar worked on that, of course. So you can do exactly, well, not exactly, but do similar things, showing the power of networks in economics. You can do centralities analysis. Centrality is probably something that is more elusive quantity in networks because it depends the kind of things you are looking for, and you have different quantities of centrality. This is the same. This is the same graph you take from Wikipedia. I mean, this is a very nice page on Wikipedia. Maybe some of you edited or some of you did this plot. And the heat map is related to the different definitions of centrality you may define there. Centrality can be the centrality in the cities. So the people, for example, living in the center of Zurich, reach by walk every other place in Zurich. You may have a closeness centrality. This is one, the quantity I'm talking about. You can consider that is central the guy who has the larger degree, the largest number of connections, and then it's pretty different. The bridging centrality. So the guys who bridge the two parts of the graph are the one with the largest value of centrality, and you can have spectral centrality like this one, and a pretty different. Point is that when you use all of them, you can clusterize quantities, and this is a paper, again, I forgot to put the authors, but I believe this is Roger Guimerà, Marta Sales. For sure, this is Universitat Rovira i Virgili in Tarragona, and this is the network, I believe, Albert Diaz-Guilera is also involved in this paper. And these are emails exchanged by people in the university, and the color is the department. Okay, and when you do this centrality analysis and you do Newman-Girvan algorithm, well, you just distinguish all the different departments. So most of the activities within the department, and there are few emails scattered along the university. The yellow one, that is the central administration. So this communicates with everybody. So networks work. Networks are very good in order to, well, I'm afraid the next one will be misplaced, some of the things, okay. But very good in detecting the complexity, but this is just one part of the story, okay? Networks are pretty good for another reason, because they visualize instantly what's going on. And visualize is not a detail. If you think about our languages that are all Indo-European in this room, mostly I would say, to see and to know have the same root, okay? So nobody knows what Indo-Europeans used to speak, but it has been supposed that this word vid, I don't know how to, nobody knows how to pronounce, but it goes in Latin, becomes video or videor. That means I see but it's also it looks appropriate. It depends, no? It's Latin is a little subtle. We still say vedo in Italian, vedere. That's still to see. Ancient Greeks say boida. Boida means I have seen, now I know. Veda, the book of Veda. Have you heard about that? The book of knowledge. But in German, but I hope to pronounce correctly, it's wissen. No, it's the same word again, to know. A man who knows in English is a wise man, no, and so on and so forth. In English, when you understand something, I mean, I've been told, I mean, I'm Italian speaker, mother tongue, but you say I see, no, when you understand something. So, and even in Chinese, something that is completely different from Indo-European, you use Ming Bai, shining white, that to say that something that is clear. No? Okay, so networks visualize things very efficiently. This is again a larger part of the DCSOM, and it is nice work by Juan Ilgo. Visualize economics. Again, Cesar, sorry, I thought you were showing economic development, but I mean, this is World Trade Web. This is a paper by Maria Angeles Serrano, Marian Bogugnano, Alessandro Vespignani that we'll hope we'll see today. And this is the trade. Oh, sorry about that. So let's see if, okay. This is the trade in the 60s. So you have hubs like United States, United Kingdom, and Federal Republic of Germany at the time, and in the year 2000. So you see the structure is, we don't know with the tariffs what will be, but I mean, this is what happened in these 40 years. And I could talk on this picture for a while because there is a lot of information. So you have hubs, and of course hubs seems to be the great players, but you have colors in the vertices. So if you're an exporter, you're green. If you're an importer, you're red. The arrows is the flow of money. Okay, so if you are an importer, like in this case, the flow of money goes outside to Canada. So maybe Trump is right. It goes to China. It goes to Japan. Okay. And you can see regions, you can see regional or political. 5 minutes, okay, I'll be very fast. Political or regional cluster that going on. And once you know the network structure of these things, well, you can describe and understand. What is very important is that you can show politics as well. These are families in the Renaissance is a very renowned example, so I can skip. In the Renaissance, families made collaboration or agreement or, by weddings. So one guy from one family, another girl from another family. At the time, it was very strict, the way you can have weddings and marriage. Must engage with each other, and this is an alliance. Okay, so you see this figure and you understand the politics. So who's the most important guy in Florence? Is Medici. Who are at the periphery? Pazzi, or these are even disconnected from the set of alliances, and this is exactly what happened. So in 1478, Pazzi tried to kill all the Medici. They didn't. They just killed this poor guy, Giuliano de' Medici. This is a picture by Sandro Botticelli. And that's it. But you don't need to be a skilled historian to understand what's going on here. So who's in charge and who wants to challenge this power there. You can see politics also now. Okay. So this is the wonderful work that David Chavalaria is doing in Paris. It's a politoscope. This is a retweeting of tweets from political parties, and you see a spectroscopy of politics in France. Okay, you go from the left to the right, and cluster of people retweeting what their political best politicians, at least what they think about the best politician think, and is their thought. So they're retweeting what they do. Okay, this is the county of Descartes, and then of course, let's go back to the country of Renaissance, so Italy. So it's much more messy, okay? So you have clusters of people or mixed. The Matteo Renzi used to be in the left, is here, and Silvio Berlusconi is here. But by the way, they're not that far from Italians, so maybe understand what I'm talking about. But if you study in the detail, well, order emerges even in Italy. So this is a subcluster of the right wing. This is neo-fascist organization, Casa Pound, and it's connected with the Northern League and to Fratelli d'Italia, maybe more to these guys than to this one. This makes sense, I mean, in Italy for people following Italian politics. So a few minutes, let me just mention what we did in finance. Okay, you can apply the network in finance as well with a pretty nice, we'll talk about that. I just mentioned the work of another guy in Zurich, Stefano Battiston, who's a driving force in this activity. And just pass to one of the fashionable things at the moment, there is digital twins. You probably know what digital twins is, so I will skip. What is important is when digital twins were introduced, they were introduced to tame complexity. There is something not particularly nice. No? This is the emergence of new unpredictable behavior from the interaction of the parts. Okay, so this was bad, and so digital twin should mitigate unpredictable, undesirable, emergent behavior in complex systems. But thanks to Dirk, this is exactly what we want, I imagine. No? So Dirk taught us that this is what we need. So let me show some of the papers we did. I did together with Dirk. So this is the role of complexity for digital twins. Instead of taming, we should put complexity into your digital twins because you would like to reproduce in your computer exactly the emergence of this unpredictable behavior. So of course, you have all the things that Shlomo talked about, so the interdependence of networks at various levels, okay? And the only way to take into account this mathematically is by network. So last slide, we need digital twins that are able to embrace the potential of complex systems, because with the combination of complex systems and the mathematics of networks and the AI of digital twins, well, we could promote what Cesar was talking about in the previous slide. So participation of the people and collaborative exploration. So let me finish with some piece of advertisement. This is a project led by Panos Argyrakis in Thessaloniki. Which kind of concept of complexity people need in the courses to get a better science, a better job. So have a look to this LEAP project, Google that. If you like Venice, don't forget to have a look to this satellite we're organizing 21st, 23rd of July. We're flexible on the dates. If you really arrive in millions, we can extend to another couple of days. This will be in the island of San Giorgio in front of San Marco. Complex networks, so shorter at, and just remember these two, or Google complex networks satellite or SatFis. Okay, you don't care about my publications. The only things we care about is happy birthday, Dirk. Okay.
All right, so thank you so much, Guido.